Hey there, this is Brandon Kish, and this is some information on the clocks built into the PIC. As I had one of the students asking me how the clocks worked and how to set them up. The first thing that I want to note here is if we look at our PDF file, the clocks are a little bit misleading. They're not technically, the timer. It's actually not necessarily a timer in the way that we think of it, but it works a little differently. If we look, we can see that the timer 0, or in fact any of the 3 timers that the PIC has, module will increment every instruction cycle. And what this means is basically every time the PIC executes a command, it's going to increment the timer, and that is what the actual timer does. Also, it has a counter mode, which also is very misleading, because the counter mode isn't something that we can use to literally as a counter. It actually is set up for something such as an external clock or synchronizing with another PIC as far as instruction cycles. And if we look at our diagram, we can see we have a pin that's a TOCKI pin, and what this does is we connect this to something else that has a clock or that oscillates, and the PIC can keep track at how many instruction cycles the other PIC has executed versus how many processes that the one with the timer has actually executed, and we can use this to compare how fast each one is running. And so that's what they're calling counter mode. So that being said, one other thing I wanted to point out, the other thing to note here is that the clock 0 and some of the other clocks have something called a prescaler. And so what this does is it's about 8 different settings that you can set the PIC to, the timer 0 or the timers to, that will have skipped the instructions. So instead of it counting every instruction that's executed, it'll count like only every fourth instruction, or maybe every 8th. And so what this can do is it can say you have a PIC that's running at 20 megahertz, for instance. You can use the prescaler to kind of trick, if you will, the timer 0 to thinking that the PIC is running at 8 megahertz. And so what this does is using something, say, as the debugger, or using a formula, you can find out how long the PIC has been executing the commands by calculating what megahertz or what prescaler you have set the clock to, and by counting the actual value of the clock, or seeing what the value of the clock is, you can actually determine how long the PIC's been, or how long it's been since you've set the clock, or the timer. I keep changing my terms here. So basically that's what a prescaler does, is it allows you, instead of to read every instruction, it allows you to skip 1 or 2 instructions and count only every other instruction, or every 5 or 20 instructions, ultimately making the clock run at a different speed than the processor itself. Timer, there I go again. Here is the timer 0 again, and we see that it has an interrupt similar to the pins that we use. So when the timer actually overflows, meaning that when the value is too great for the timer to count anymore, which timer 0 is actually an 8-bit timer, meaning that its total value that it can hold inside of its memory is 255. So once it reaches the value 255, it overflows. The data is too great for it to be able to be held anymore. So that's what they're talking about here when the register overflows. When this happens, it will set the timer 0 interrupt bit. And anyone that's using interrupts, you'll notice that you have a command that says T0IE, which we set to 0 to turn that interrupt off. Just in case for some reason your timer started, you won't get interrupts based on that timer. Okay, some other things to note about the different timers. And I'll be honest, I'm not 100% sure about how the timers work or their exact purpose or function. But from what I can understand, you actually technically have 4 timers. 3 of them are used to count or to keep track of how many cycles the PIC has ran. The 4th one is called a watchdog timer, and it works slightly different than the other timers. As you can see here, as conditions that cause the PIC to reset, you have something called the WDT, which is the watchdog timer. And the watchdog timer will actually reset the PIC either during sleep or during normal operation. So I'm not exactly 100% sure how you reset with the watchdog timer. I believe it's a set variable. So I think it's like something like 8 milliseconds, that once you activate the watchdog timer, it takes 8 milliseconds and then the PIC restarts, kind of like pressing the restart button on your computer. So this might be useful for something, say if you wanted to, once your PIC completed a certain operation or it was successful in something, to either shut down the PIC so it does not continue operating, or to even reset it, to restart it to do the same process, but maybe on an assembly line you're trying to do, another piece of work or something, and you want it to reset before it starts operating. So to do this, you would enable the watchdog timer and go through the setup or the settings for the watchdog timer, and that would allow it to reset. Timer 1 is a little bit robust. It's a little bit does quite a bit more than the other timers here. See, I'll scroll down and you should be able to see. Basically, timer 1 is designed to also synchronize with another PIC. In fact, I believe timer 0 is more for like something that a device that oscillates, that you can keep track of how many times it's completed the task externally. So like, I don't know, say if you had a sensor or something and you wanted to count how many times it read something, you could use timer 0, whereas timer 1 is more for actually talking to another PIC and synchronizing the two PICs together. So say you needed more output pins, or you need more input pins, or maybe you had 2 separate processes altogether, but you wanted the 2 separate PICs to keep track of where each other was during that process. You could use timer 1, which I would have to look at which pin it's connected to, but it allows for synchronous or asynchronous operation. It also has an interrupt on overflow. This clock can actually wake up your PIC if you put it into sleep mode. Wake up on overflow. So it would wake up once it overflowed there. And it's also, instead of it being an 8-bit timer, it's a 16-bit timer. So we have almost double the capacity there, if not significantly more that it could count up to or count down from. So as we mentioned, the prescaler before, clock timer 1 also has a prescaler. So we can also see here the timer 1 interrupt is caused by on a rollover. So basically when it overflows, or when it rolls over to the following address, I believe they call it rollover here because since this is a 16-bit timer, you're actually talking about 2 separate memory addresses. So it doesn't quite make sense to say overflow, because one of the registers is always going to overflow into the second register so that you can count up to greater numbers. So I believe that's why they use the term rollover for your timer 1 interrupt. So here we can see timer 1 is actually the first timer that we're looking at here. We can actually say set a particular time that we want to count up to, and have timer 1 tell us that it's reached that time. You can see here the way we do that is we use the CCPR1H. So whoops. And the CCPR1L, and what this does is the PIC compares the value in these 2 registers to the 2 values of the actual timer itself. And once the timer is equal to the values inside of the CCPR1 registers, the address and the location of one of the bits inside of a register, and I'm not sure which, but I'm sure if you searched CCP you'd find which register this pertains to. But it's similar to like the interrupt, where once those 2 values are equal, this this bit here, the CCP, will equal 1. However, it does not actually interrupt. It does not cause an interrupt flag to flag up. It's its own flag, and it allows the timer 1 to continue counting while those conditions are true. So it does not actually stop the timer. And if we look at timer 2 is also capable of not only causing an interrupt bit to turn on, but it also has its own separate bit that we can use to compare values similar to timer 1. So this PR2 bit will actually activate when the 2 values are the same. And just like similar to the first timer, we have actually this timer is more of an actual timer itself, where you're comparing two values. However, the register is still only 8 bits, unlike timer 1 that's 16, so the maximum value you can count up to is 255. So I hope this kind of helps understand the timers a little bit. I know I didn't really go into the code very much, because to be honest, I don't think anyone's going to want to use this after it's been explained. But if people still want to see what the code would look like, or would like me to figure it out, just either send me an email or maybe even comment. I'll see if there's any comments for it. So, and to be honest, I'm not 100% sure exactly how these timers work, so I might be wrong about some of the information that I've given inside of this video. And if I am, please feel free to email me or comment below listing some of the mistakes I might have made. Like I said, I'm not 100% sure exactly how the timers work, but from what I'm reading, this is just the information that I've gathered, and kind of give you an idea of what they do and how they operate. So for now, I'll see you guys later.